Okay, so welcome back to this next video in which we are discussing group homomorphisms. Okay, so in the previous video what we saw is the definition of a group homomorphism, and we saw how the definition of a group homomorphism is really a generalization of the concept of a group isomorphism that we've seen in previous videos. Okay, so a group homomorphism is a mapping which we've called phi from one group, which we'll call the domain group capital G, to another group which we'll call the codomain group capital G prime. So basically it's a mapping which will ascribe to every element of this domain group capital G an element in the codomain group capital G prime. Okay, now the special property then that this mapping has to obey is this property of homomorphisms here, that phi of A composed with B is equal to phi of A composed with phi of B, and that has to be true for all little a and little b is an element of capital G, okay, the domain group. So what does that really actually mean? That means that if you take any two arbitrary elements of this group capital G, then what you can do is you can compose those two elements together in the domain group capital G to get an answer which is A composed with B here, and then you can take phi of that answer. Okay, so you can map this answer into the codomain group G prime to get some answer in the codomain group G prime over here, which is phi of A composed with B. Or you can do it the other way around. You can firstly map A and B into G prime, okay, the codomain group, to get phi of A and phi of B, and then compose these two answers together in the codomain group G prime, and you'll get some other answer in the codomain group G prime. And basically, if this mapping is a homomorphism, it has to be the case that these two sides are equal to each other. The two ways of doing this are equal to each other, i.e. it does not matter whether you first compose and then map, or first map and then compose, the answer is the same, basically. Okay, right. So we've discussed then that a bijective homomorphism is actually an isomorphism. However, the big generalization here is that homomorphisms don't have to necessarily be bijective. Okay, so all group isomorphisms are group homomorphisms, but not all group homomorphisms are group isomorphisms. Okay, right. So then what we did in the previous videos, we discussed the two reasons that a mapping phi, a group homomorphism, can fail to be bijective. So there are two reasons that it can fail to be bijective. One, that it fails to be surjective, or two, that it fails to be injective. Okay, so let's just go over what surjective means. Surjective means that every element in the codomain group must have an element in the domain group being mapped onto it. Okay, so if a homomorphism is not going to be surjective, then that must mean that there is at least one element in the codomain group G prime here that does not have an element in capital G, the domain group being mapped onto it, basically. Okay, that's what's meant by a non-surjective group homomorphism. Okay, and as we'll see in this video, non-surjective group homomorphisms can always be reduced to thinking in terms of a surjective group homomorphism. So we're going to see that this isn't a very interesting way for a group homomorphism to fail to be bijective, and in fact we can always go from thinking in terms of a non-surjective homomorphism to thinking in terms of a surjective homomorphism. So we can always reduce this to a surjective homomorphism, and I will explain how in this video. Okay, right, so we'll come back to that. Okay, now the second and more interesting reason that a group homomorphism can fail to be bijective is that it fails to be injective. And injective is the fancy word meaning one-to-one, basically. Okay, so if a mapping is one-to-one, it means that any element in the codomain group which does have an element in the domain group being mapped onto it, so any element in the image of the homomorphism, which is just the subset of the codomain group that actually does have elements being mapped onto it, okay, any element in that, if the mapping is going to be injective, needs to have just one element in the domain group being mapped onto it. So you can't have loads of elements in the domain group being mapped onto one element in the codomain group, basically, if the mapping is going to be injective. So if a group homomorphism is not injective, then that will mean that there are elements in the image of the homomorphism that have more than one element in the in the domain group being mapped onto them, basically. Okay, and as we'll see, that's the more interesting reason for which a homomorphism can fail to be bijective. Okay, right. So what do I want to do now then? What I want to do is talk about why it's the case that if you have a non-surjective homomorphism, you can always reduce that into thinking in terms of a surjective homomorphism. Okay, so what I actually want to show you is that you can always reduce a non-surjective homomorphism between G and G prime into a surjective homomorphism from G to the image of the homomorphism. Okay, but before we get to that, what I need to do is explain to you a few little nuggets of information, basically, a few nuggets of theory regarding homomorphisms, so that we can get to that point where we can explain why we can reduce a non-surjective homomorphism into a surjective homomorphism. Okay, so the first little theorem then that I want to prove about homomorphisms then is that any homomorphism phi will always map the identity element in the domain group, which I'll denote E and then subscript capital G. So this just means the identity of the domain group. It will always map that into the identity element, or rather onto the identity element in the codomain group, so E and then subscript G prime. So I want to prove that this is true, basically. So if I draw a picture for this, okay, we'll have our two groups once again. Okay, and I'll just make sure this is straight. There we go. Okay, so this is our domain group, capital G here, and here's our codomain group, capital G prime here. Okay, and basically this theorem says that the identity in capital G, this element here, will be mapped onto the identity in capital G prime. Okay, this is what we want to show always, basically. Okay, so let me just color code this in. So here is our domain group, capital G here, which we've always denoted in red, and here is our codomain group, capital G prime here, which we've always denoted in green. Okay, so we want to be able to prove this. Now, how are we going to prove this? Well, the only thing that we can possibly use, because it's the only thing that we're given, is that property of homomorphism. So somehow we have to use the fact that phi of A composed with B is equal to phi of A composed with phi of B for all little a and little b is an element of the group capital G, the domain group. That's all we have. That's all that is special about a homomorphism. Otherwise, it's just an arbitrary map between two groups. Okay, this is what makes it special. Okay, so the only way we could possibly prove that in the case of all homomorphisms, the identity is mapped onto the identity is using this property here, basically. Okay, right. So, let me explain how we're going to do this. So we're going to use a little bit of background theory which applies to applies to a general group, basically. Okay, so this is the little background piece of understanding that you need to have in order to be able to prove this. And I should stress that there are many ways that you can prove this, but in my opinion, one of the most simple ways is the method that we're going to use. Okay, so just a little sort of side bit here then. Okay, so if we're working in an arbitrary group, let's say little g, okay, and I have an element, let's say little x, which is an arbitrary element of the group, which I know obeys a certain equation, and the equation that it's going to obey is that x composed with x is going to equal x. So this element, little x, whatever it is, composes with itself to give itself back again. Okay, so x obeys this equation, basically. My claim is that if I know that x obeys this equation, there is only one element of this group, capital G, okay, and this is an arbitrary group, capital G, that can possibly ever obey this equation. So there's only one element of a group that can ever compose with itself to give itself, okay, and that's the identity. So my claim is that the only solution to this equation is that little x is equal to the identity in our group, basically. Okay, now how do you show that? Well, very simply. Okay, all you need to do is compose on both sides by little x inverse. So because we're working in a group, what I can do is compose on the left, let's say, on both sides by little x inverse. On this side, the little x inverse will cancel with one of the little x's here, so I'll get little x left over on the left hand side, and on the right hand side, little x composed with little x inverse is equal to the identity element, so I'll just get that little x is equal to the identity element basically. Okay, and there is the solution to that equation, the only solution in the group to that equation. So basically what I have just shown you is that the only element of a group that can compose with itself to give itself back again is the identity element. Now what use is that to us? Well, what I am trying to show you is that phi of the identity in the domain group, capital G, is equal to the identity in the codomain group, E at G prime here. Okay, so if I could show that this element, phi of the identity of G, composes with itself in the codomain group G prime to give itself back again, then I would have shown that this has to be the identity in G prime. Okay, so what I'm going to consider is what is phi of the identity of G composed with phi of the identity of G. All I know at the moment is that whatever phi of the identity of G is, it is an element of G prime, basically. Okay, because quite simply, I'm taking the identity in G and mapping it onto an element in G prime. So whatever it is, it's an element of G prime. So I can compose it with itself in G prime, and my strategy here is to show that this actually composes with itself to give itself, and hence this must be the identity in G prime, because that's the only solution for that equation, basically, in any group. Okay, right, so how then am I going to work with this? What is phi of the identity of G composed with phi of the identity of G? Well, I must at some point use this, because this is all that's special about homomorphisms, so let's use this now. Okay, and what I'm going to do is use it backwards. So we've got this side basically, and I'm going to turn it into this side. So I can now rewrite phi of the identity of G composed with phi of the identity of G as phi of the identity of G composed with the identity of G, where now we're composing the identity of G with the identity of G in the group G here, the domain group. Okay, now of course when you compose the identity in G with the identity in G, you get back again the identity in G. So the answer here is just the identity in G. Okay, so now what I have just shown you then is that phi of the identity of G composes with itself to give phi of the identity of G, basically, which is exactly what I needed to show. Okay, I have just shown that whatever this element is, phi of the identity of G, in G prime, it composes with itself to give itself back again, and now there's only one element of the group G prime that can possibly do that, and that is the identity of G prime. Okay, so what I've just shown you then is that phi of the identity of G must equal the identity in G prime, basically. Okay, so that's theorem number 1 proven then, that any homomorphism will always map the identity in the domain group onto the identity in the codomain group. So that's a useful little piece of understanding that we now have about homomorphisms, that the identity in the domain group is always mapped onto the identity in the codomain group. No ifs, no buts. If it obeys this, it has to obey this as well. Okay, so that's excellent. There's another theorem that I want to show you now, okay, which is that if we have an arbitrary element, let's say a little a, which is an element of our domain group, capital G here, okay, then what we know is that little a will also have its inverse within capital G, because of course capital G is a group, so little a will also have an inverse. Okay, so let me just draw a picture for this. So here is our domain group, capital G here. Okay, and I'll colour this in red. And we will have these two elements in capital G. So we'll have little a, an element in capital G, and we'll also have little a inverse, which is an element of capital G. Again, of course, it's not necessarily true that they are distinct elements. They might be the same element, but we're going to see that that won't really matter. Okay, the picture obviously suggests that they're distinct elements, but what we're going to show it will apply even if they're not. Okay, right. So, what then is the theorem that I would like to show? Well, I would like to show basically that phi of A inverse is equal to phi of A inverse. Now, what does that actually mean? Well, it's best shown with a picture. Okay, so now what we're going to have to do is put in the codomain group. So since we're talking about the homomorphism, we need to have the other group that's involved in the homomorphism here. So we need to have our codomain group G prime here. Okay. And basically what we know is that both of these elements, A and A inverse, whether they're distinct or not, will be mapped onto elements in G prime. Okay, so here we'll have A being mapped onto phi of A here, and we'll have A inverse being mapped onto phi of A inverse. And again, my picture suggests that these are distinct elements. Phi of A and phi of A inverse are distinct elements, is what my picture suggests. But they might be the same element, even if these two here are distinct elements in G. Because we know the homomorphism isn't necessarily injective, it could be the case that even though these two are distinct in here, they might be mapped onto the same element in here, basically. Okay, so although my picture suggests that these are distinct, it might not necessarily be the case. Okay, but again, it won't matter for our argument. Okay, so what does this theorem actually say here? Well, it says that this answer here, phi of A inverse, okay, what A inverse is mapped onto by our homomorphism phi here, okay, this is actually going to be equal to the inverse of phi of A in G prime. So basically what this equation here is saying is that these two here, phi of A and phi of A inverse, are each other's inverse in the codomain group as well as in the domain group. So what it's really saying is that inverses remain inverses under the homomorphism. Okay, so phi of A inverse will compose with phi of A to give the identity in G prime, is what we're effectively saying. That phi of A inverse here is actually equal to the inverse of this element in G prime, which we would call phi of A inverse, like so. These two are inverses. That's what I want to show, basically. That's what this is saying. Okay, right. So how do I show that then? Well, what I need to show then is that these two things will compose with one another to give the identity in G prime, basically. Okay, so what I need to ask is what is phi of A composed with phi of A inverse? Is it going to equal the identity in G prime? Okay, because that's what they need to compose together to give if they're going to be each other's inverse in this codomain group, basically. Okay, so once again, there's only one thing that I can use here, which is that property of homomorphisms. Okay, so what I need to do is combine these two things together, again using the property of homomorphisms in reverse. So basically, I'm starting off with the right-hand side here, and I need to turn it into a left-hand side here. So what I'm going to do is I'm going to rewrite this now as phi of A composed with A inverse, like so. Okay, and then of course I can compose A and A inverse together in my domain group here, which will give me the identity in G. Okay, and then of course we know that phi of the identity of G is just equal to the identity in G prime. Okay, so now I do indeed know that phi of A composed with phi of A inverse is going to give the identity in G prime. Okay, and of course you could do this the other way around as well, so you could compose phi of A inverse, okay, with phi of A, and you'd be able to do exactly the same thing. So if you compose them the other way around, you'd again be able to combine them together. You'd get the A inverse and the A the opposite way around, but of course we know that because A and A inverse are inverses in the domain group, that it doesn't matter which way around you compose them together, it still gives the identity in G, and therefore again you'll get the same result. Okay, so you can quite easily show that these two things, phi of A and phi of A inverse, will compose with one another either way round to always give the identity in our codomain group G prime, basically. Okay, so what we have just shown is that inverses in the domain group will be mapped onto inverses in the codomain group at G prime over here. Okay, right, so those are the two little facts that we need to understand in order for me to now discuss what I want to do now. Okay, so what we're going to do is we're going to show that the image of a homomorphism is actually a subgroup of the codomain group, and then what we'll see is that we can think of a homomorphism that is non-surjective as being a surjective homomorphism from the domain group G onto the image of that homomorphism. But I think actually we'll have a break here and we'll do that in the next video.